So this is the joint work with Ashish and Kevin. So this is the outline of my talk today. So first I'm going to introduce some background on Decipherment. And then I will explain the motivation of this work and what we have contributed. And then after that, I'm going to talk about some details about this work. And then at the end, the conclusion. So what is actually Decipherment? And here is an example of letter substitution cipher. So on the screen, you can see a snippet of English, and we call this plain text. And now, someone goes through this plain text and replace each letter with a unique cipher token. And we're based on some substitution table that you don't know about it, and then turn this plain text into a cipher text. And so then what Decipherment is all about is to, given this ciphertext, you're trying to recover the substitution table that is now showing on the right-hand side of the slide, and as well as the plain text itself. And here is just another example of the substitution cipher. It's called word substitution cipher. So it's exactly the same as letter substitution cipher, except that the unit of substitution becomes words instead of letters. And then the reason that we are very interested in this kind of cipher is because essentially very similar to translation, as in translation there's also a large number of word substitution. So and we hope that we have the ability to solve this kind of cipher, we'll be able to use it to help improve machine translation. And so now we know what the decipherment is, and then let's look at how we can solve this problem automatically. So here we use a noisy channel model. So according to this model, ciphertext is generated in several steps. So first we have the model of the plain text that generates some plain text with certain probability. And this plain text goes through a noisy channel. And here is a simple substitution with the probability of ciphertext given the plain text. And then we have the ciphertext that we observe. So given this model as this way, how we are going to solve a cipher. So first of all, we're going to learn the model of the plain text with a large amount of the plain text that is unrelated to the ciphertext. And then we use EM to search the probability of the cipher given the plain text so that the likelihood of the ciphertext is maximized. And note that the time complexity of this approach is n times v squared times r, where the n is the length of the ciphertext, and v is the vocabulary size, and r is the number of iterations you need. And now let's look at the motivation of this work. So in previous work that our work shows that the decipherment can be used to improve machine translation. And here is just a graph of the pipeline of the state-of-the-art machine translation systems. So you have the parallel data, and then you do the word alignment, and then you have the translation table, and this translation table can be used as a language model during the decoding process. And now we have some non-parallel data here, and then you can use some seed on the translation table to initialize the decipherment process. And then you can learn a new translation table from the decipherment. And this translation table can then be either used to improve the word alignment together with parallel data, and also the new translation you learn can be used through the decoding process to translate any words that you never observed in parallel data. And we can see that the two processes has close relationship with each other, but the training are separate. So the idea here is that whether we can have a method to combine them and to learn them at the same time, to perform word alignment and decipherment jointly. And so motivated by this idea, we propose a new framework to perform the joint word alignment and decipherment. And in the experiment, we showed that the joint framework improves both word alignment and translation quality significantly. And in the end, last but not least, we released some Malagasy feedback, as well as about 50 million word Malagasy news data for future research use. And now let's go into the details of this work. So first, now let's look at what actually word alignment model is doing. So for the word alignment, the input of the model is a bunch of number of parallel texts. So we have foreign English sentences out, and English foreign sentences out, and English sentences in. And the output of the model is the word alignment between those sentences. So the model has two sets of parameters. So one is the distortion probabilities, and the other is translation probabilities. And the objective here is really to maximize the likelihood of the parallel data by tuning those parameters. And here is the decipherment model. So for the decipherment, the input will be a number of foreign text migrants, dependency migrants. So we use migrant here as we follow the previous work using the dependency-based decipherment. And then the output of the model is actually the decipherment, English decipherment of those foreign dependency migrants. And here we'll use the dependency language model for the task. And this dependency language model is created from dependency trees. And then on the right-hand side, you can see the objective of the decipherment model. It only has, since the language probability is already fixed, it only has one set of parameters, and they are translation probabilities. And the objective of the decipherment model is to maximize the likelihood of the monolingual data that you observe. Here is just the number of dependency migrants. And now we know two models, and let's look at both of them at the same time. So on the left-hand side is the word alignment objective, and the right-hand side is the decipherment objective. And you can easily observe that the two models share parameters, and they are translation probabilities. And so based on that, we propose to maximize the likelihood of the parallel data as well as the likelihood of the monolingual data at the same time. So the new objective is the probability of the parallel data plus alpha times the probability of the monolingual data that you observe. And we can use EM to perform the search. So at the very beginning of the iteration, we start with only parallel data. So we run 5 separate iterations in 5 iterations on the parallel text only. And then for the E step, and then we start the joining process. So for the E step, we collect the expected counts for the translation probability from the non-parallel data. And we also collect expected counts for the translation parameters and the distortion parameters using parallel data. And before we normalize them, we actually sum them up first, sum up those expected counts. And then we do the normalization to update those parameters. And then the next step, we just repeat the same process. So we will know that the E-step model for the parallel data has been well studied. So the problem is really on the non-parallel part. So on the non-parallel data, as since it's decipherment, as I mentioned, so the time complexity of this approach is n times v squared times r. And what we here is the vocabulary size, and n is the number of ciphertext. And it's all very clear that it's not really scalable for those b and n becomes very large. And this is often the case when it comes to deciphering language. So instead of so on the non-parallel data, we propose to use sampling techniques to collect the expected counts. And here we're given a cycle diagram F1, F2, and then we use light sampling to draw samples, E1, E2, according to its posterior probability. And here, that n is the total number of samples that we draw for this cycle we use this because we want to simulate the low density results, which is ultimately of this work. And we also have much larger amount of non-parallel data, 80 million for Spanish and 400 million for English. Since we also need to we do candidacy-based decipherment, we need parser to parse all this monolingual data. So we have Spanish parser as well as English parser. So the Spanish parser is trained using 0.4 million token of data, and English is trained using approximately 1 million data. And here is just the learning curves for the alignment experiment. The y-axis here are alignment absolute, and the x-axis here are number of iterations. And the black line indicates the baseline, which use just the EM process of parallel data only. And the red line here is the joint process. And you can see from the graph that the joint model outperformed the baseline for both model 1 and HMM model. Okay, so everything goes good so far, and the joint process does improve this model alignment quality significantly. So the question left is, Spanish is still not a low density language, so we want to see whether this approach can really improve translation in a real low density language settings. And we choose to work for Malagasy. And I'm going to talk about it. So the Malagasy language is the official language of Madagascar. It's totally okay if you don't know where this country is. I'm going to show it in the next slide. So Madagascar is a country in Africa, it's shown in this slide. And so although it's spoken in Africa, Malagasy has its root in Southeast Asia. And has approximately like 18 million native speakers. And it's also a happy mixture of language, which means that the verb comes first and followed by the object and then the subject. What English has an SVO word order. And remember, since the decipherment here needs a dependency parser, we wanted a good dependency parser from Malagasy. However, since this is really a low density language, it doesn't really have any training for it. So initially, we only have about 120 sentences between Malagasy parser. And just a reminder that the Spanish parser is actually trained on 400,000 tokens instead of only 20,000 tokens. So initially, our parser has resolved about 72.4 direct attachment accuracy on a test set. So more data definitely leads to better parsing accuracy. So how are you going to obtain more data? So the idea here is actually to use parallel data. So we extract some subset of the English Malagasy parallel data we have, and we use the English parser to parse the English part of the parallel data first. And we also use the initial basic parser to parse the Malagasy data. And then we went to manually correct those mistakes made by the Malagasy parser. So the way we correct it is actually by looking at the parsing results from both sides, and also looking at the parallel data, and then manually project those dependency relationships from this English to the Malagasy trees. And through this approach, we are able to improve the parsing accuracy to 80% from 72%. And now we finally have a reasonable parser with reasonable accuracy. Now let's look at whether it has effects in machine translation. And here's the data we use for machine translation experiments. So similarly, for parallel data, we have a small amount of parallel data for Malagasy and English, of about 1 million tokens for each. And then we have a much larger number of non-parallel data. Here for English, we have 834 million of non-parallel data for the gigawatt. And we also have a large amount of non-parallel data that's collected on the website. So for Malagasy, we manually collect 15 million of tokens of news data on the local website, as well as 400 million tokens for English from the All Africa. It's an African news. And in the experiment, we evaluate three systems. So the first is the baseline, which is range-based machine translation system, it's Moses. We run model 1 to 10 iterations, and HMM for 5 iterations. And we didn't use model 3 and model 4 because we didn't find the improved score significantly. We aligned the corpus in 2 directions and used row that final to extract the traces. And the second system to compare is the joint system. So we run 10 iterations for model 1. The first 5 iterations only with parallel data, and then the next 5 iterations for model 1 is joint process, and then another 5 iterations for HMM. And we align extract traces only on one direction here, which is English given the Malagasy. And in the end, is the third system to compare is our disjoint approach. Since I talked about it in the very beginning, I'm not going to talk too much details about it. And here's the other results of the in-domain on the global voices test set. On the y-axis is the blue score, and the gray bar here is performance of the baseline system. And the yellow bar here is the performance for the district system. And the blue bar here are the results from the joint process. You can see while the district process here doesn't show a very significant improvement compared with the baseline, the joint process does a much better job. So it improves about 0.9 improve score from the baseline system on the test set. And here just another results on another domain, which is the test set on the local news. And similarly, we didn't see a very significant improvement on the disjoint approach, but see a much larger gain when we perform the joint decipherment and alignment. Here's the conclusion. So we propose a framework for joint alignment and decipherment. And we see that the joint process improved both alignment and machine translation quality significantly. And in the end, we released the meaning Malagasy tree value and 15 million of tokens of Malagasy news website for future research use. Here, this concludes my talk. I'm very happy to take any questions. Thank you.
Yeah, thanks for next talk. And any comments or questions?
So, thanks for a nice talk. So I'm wondering, maybe I missed something, but you're using the same table for the decipherment, like translation table, as the translation model. Is that true, or did I misinterpret you?
The question is whether I use the same translation table.
Yeah. Yeah, you're training the same table, or did I get it wrong?
They share the probabilities.
They share the probabilities, but they're not the same. Okay.
Well, it's exactly the same. Yeah.
Okay, so here's the next question about the joint training. I'm wondering, why did you choose for summing the likelihoods? This is a linear interpolation of 2 likelihoods, and you're optimizing that. Is there a reason to choose that, for example, over seeing it as a concatenation of 2 corpora, the parallel corpus and the linear corpus, and then multiplying the likelihoods, scaling with a power?
I think
so
it's the sum up is this is a lot linear. Yeah, it's a lot linear.
Okay, the log linear. Okay, that's the same. So the same. Okay, I got it now. Thanks. Yeah. Okay.
Hey, I'm just wondering what happens if you just initialize the decipherment with your parallel data and then just ignore the parallel data from there on and just do decipherment and take the result and see what happens. Does that work?
That's a disjoint approach. So we showed that the disjoint approach is not doing quite well.
So no,
because the alignment with the little parallel data really doesn't give you a UC table, so that's probably the reason.
I think there's a single hyperparameter alpha, so how sensitive it is?
It is,
That's balancing bilingual and monolingual.
Depends on, also depends on how much like the parallel data you have and also the non-parallel data you have. So we actually did a search using the development set to search for the best set of algorithms.
And I also noticed that there's a large difference in the corpus size in the Spanish and English and the Spanish and Madagascar. And is that very popular in this setting? Because I'm not familiar with this kind of decipherment problem. So. And the size is totally different. Monolingual data size is totally different. And it's quite amazing that it works quite well, even such a large difference.
With not much, so the problem here is that for Spanish English, we easily can collect large number of monolingual data. So there's a lot of them. But for the Malagasy, it's really hard to collect even more monolingual data. So like 50 million is we spend like about 2 months to collect those monolingual data. And so that's why they have. You see that there's a very different setting. So that is not like purposely we choose that. It's just the ability that we probably don't have lots of time or like resources to collect even a large number. With more monolingual data, I'm confident that the result is probably going to be better. And yeah, thank you.
Okay. And any other comments, questions?
So do you have any number about the number of new phrase results from decipherment use in decoder?
Oh, in this work actually we didn't use the auto vocabulary thing in the final decoding phase, and but that's our future work too. Yeah. So in this work,
So one thing that is not completely clear to me is the relation between the monolingual data and the parallel data. Is there any constraint on how they should be related in terms of domain, genre, and that kind of stuff?
we haven't done the research yet, but that's a great question. It's a good question.
Okay.
It's
Yeah.
really investigation.
Thanks. Yeah.
Okay. Is that time for speak again?